By convention, reaction quotients and equilibrium constants, therefore, are expressed as unitless quantities. You may ask how that's possible, because we've said that the reaction quotient is expressed in terms of a ratio of product concentrations to reactant concentrations, and concentrations have units. Therefore, we're going to have to express these concentrations in terms of unitless quantities, and the way we do that is by using activities. Activities are nothing more than a ratio of a concentration relative to some standard concentration. And so to define activities, we're going to need to define what a standard concentration is. For solutions, we define the standard concentration in terms of the molar concentration. And by convention, we have set the standard concentration for solutions to be equal to 1 molar. For gases, the concentration is proportional to the pressure divided by RT, the temperature. And so, in general, we express the concentrations of gases in terms of their pressures. And so, the activity for a gas is going to be the pressure of that gas divided by the standard pressure, and the standard pressure is defined as 1 bar. Finally, for pure substances, we're going to define the activity as equal to 1. Now that we have an understanding of activities, we're ready to see how we can use those to write a mathematical expression for the reaction quotient or the equilibrium constant. To do that, we're going to use this example of a reaction between calcium carbonate solid, aqueous HCl, to form CO2 gas, water, and aqueous calcium chloride. Let's take a moment to visualize what that reaction system, that equilibrium system, would look like once it comes to equilibrium. We can see that we have a little chunk of calcium carbonate solid on the bottom of the beaker. And that solid is a pure solid. It consists of calcium cations in green and little carbonate anions around those in a regular array. So we have our little chunk of solid here. And then we have aqueous HCl. The thing to remember is that when I put HCl in water, I actually get H3O plus ions plus Cl minus ions. And so I can see in this solution that I have some waters that have an extra hydrogen on them, an extra H plus, so H3O plus, there's my H3O plus, and I have chloride ions, these yellow chloride ions, floating around in the solution. And so my HCl is represented by the H3O plus aqueous and the chloride minus aqueous. Then I have, on the product side, some CO2 gas, and so I see in my system CO2 gas that is above the solution. It has escaped the solution. It's in the gas phase above the solution. And then I have a whole lot of water because my solution is aqueous, and so I have lots and lots of water. And I have calcium chloride aqueous, and that's an ionic compound that dissolves in solution. So I have green calcium 2 plus ions and yellow chlorine minus ions that represent the calcium chloride aqueous in my solution. And so I have all the components of my reaction depicted in this picture. This is going to be helpful because when we want to write the reaction quotient, we are going to remember that we need the activities of the product molecules. So I need the activity of CO2, I need the activity of water, and I need the activity of the calcium chloride. And then I'm going to divide that by the activities of the reactant molecules. And so I need the activity of the calcium carbonate, and then I need the activity of HCl, but every reaction has 2 HCl molecules in it, and so I need to have that activity multiplied twice or squared. So now I need to figure out how I write the activities of these different species. So the first thing I'm going to recognize is that the calcium carbonate is pure. And we said that the activity of pure substances is 1, and so that is just going to be 1 in my expression. It's going to be equal to 1. Furthermore, I can treat the water, which is the solvent for this reaction, as pure, because there are so very, very many water molecules relative to the number of solute molecules in my solution that I can approximate the water, the solvent in this reaction, as being pure. And if the water is pure, then its activity is also equal to 1. And so that's going to simplify my expression quite a bit. And I'm going to be able to write that Q is equal to the activity of the CO2. But the CO2 is a gas, and so I'm going to express that in terms of the pressure of CO2 divided by the standard pressure, times the activity of the calcium chloride, which is an aqueous molecule in solution. And so I'm going to write that as the concentration of calcium chloride divided by the standard concentration. And then I'm going to divide by the concentration of HCl divided by the standard concentration for the activity of HCl. And that needs to be squared, remember, because I have 2 HCl molecules in every reaction. So this would be the reaction quotient, but we tend to use a shorthand and recognize that these standard concentrations and pressures have been judiciously defined to be equal to a numerical value of 1 as long as I use the right units. And so because all of these have a numerical value of 1, when I divide by 1, I don't change the numerator, and so I can shorthand this to write that it's equal to the pressure of CO2 times the concentration of calcium chloride divided by the concentration of HCl quantity squared. I just have to remember, if I use this shorthand notation, to make sure that everything is in the right units, because this will not work unless my pressures are in bars and my concentrations are in molar concentrations. Finally, if I want the equilibrium constant, I have exactly the same mathematical expression, but the quantities that I use for my pressures and my concentrations need to be the equilibrium concentrations and pressures for the reaction at equilibrium. And so the equilibrium constant expression represents the ratio of reactants to products at equilibrium.